everyone. So as Xavier said, I'm going to introduce Aeneas, which is a new verification pipeline for safe Rust programs. I'm going to skip the presentation of the language. The only important thing is that we'll use this following very simple example throughout the presentation. So this choose function, which takes as inputs a Boolean and 2 pointers, and depending on the value of the Boolean, returns one of the 2 pointers. And we use it the following snippet of code, where we call it by giving it mutable borrows to those X and Y variables, performing some in-place updates, and then ending the borrow Z. And the important point, of course, is that in order to make this borrow check, we need to link the output borrow to the input borrows with this alpha lifetime. Okay, so the point of this framework is to do like some of the frameworks try to do, to leverage the Rust type system to simplify reasoning about memory analysis, and so to ease verification. And of course, there are several other frameworks which have been working on this problem during the past few years, like Prusty, Crusoe, Varus. And the interesting thing is that most of those frameworks target one point in the design space. So typically they work by requiring the user to input an annotated Rust programs, so annotated with typically preconditions, postconditions, loop invariants, and cause variables. And then by using this annotated program that generate a formula, typically a weakest precondition, and then send it to an SMT solver, which then says, yes, everything is fine, or no, there's a problem, or I don't know, please provide more information. And of course, they leverage the Rust type system in different manners in order to generate this formula and make the proof obligations simpler. Now, this gives us a proof experience which targets intrinsic proofs, by which we directly add annotations in the code and then do the proofs in one go, and high automation by using typically SMT solvers. But the thing is, there are other points in the design space which are interesting to explore. So for instance, what about extrinsic proofs, by which you have a model of the program you want to analyze, and then on the side, you write and prove lemmas about this model in an extrinsic manner. And what about having less automation, but a more controlled one and better interaction by using tactics? And this is the point in the design space that we decided to explore. And it's really complementary from this work I put on the left. So what we did is we implemented a new pipeline, which is called Aeneas, which takes as input a Rust program without annotations and leverages the Rust type system to compile this program to a pure executable model. And then once you've got this model, you can extract it to various backends. And once this is done, you can write and prove lemmas about this model to prove various properties in an extrinsic manner. Now, in practice, this is actually similar to a previous work called electrolysis, and which targeted lean. And what we're trying to achieve here is to have something more flexible, which targets more backends, not just lean, and also more systematic and principled, so that on the long term we can support a bigger subset of Rust. Now, this should give you a good high-level idea of what we're trying to do. And a very natural question from there is, what does this pure executable model look like? What does this translation give you? And for this, let's look at the choose example I showed earlier, and let's do the translation step by step. So the beginning is very simple. We just introduce some X and Y variables, which I call to 0 and Y. And upon calling choose, we introduce a Z variable whose value is computed by using this purified version of choose. So this is just choose, but where we remove the borrows because they don't make sense in the pure world. And now we can look at the update which happens here. So this is an in-place update. Here we actually update X. But the thing is, because of the lifetime constraints, for as long as Z lives, we don't have access to X and Y. So in a sense, Z gives us a view over X and Y. And because of that, we don't have to take into account the effect of updating X yet. So all we have to say here is that Z gives us access to some value, which from this point onwards is equal to 2. So we say let Z equal 2. And then comes the interesting part. Here we access back X, which means we need to end the borrow Z. And so at this moment, we get access back to X and Y, and we observe the modifications which have been performed. So what we say is, we say, okay, from now onwards, X and Y have some new values. And now, what are those new values? Well, it's actually pretty simple because as the Boolean here is true, here we returned X. So through Z, we updated X, and Y is left unchanged. So the new value for X is the last value for Z, and Y is left unchanged. But this is the case only because the Boolean was true. If it were false, we would have the opposite. X would be left unchanged, and Y would be updated. So if we write this in a more general way, we get the following. If true, then what we had before, otherwise the reverse. X is left unchanged, and Y is updated. Now, what we see something which appears here, which is that upon calling choose, we had to compute some value for Z from the inputs we gave to choose. And then, so we go from the inputs to the output. And then later, upon ending the lifetime alpha and observing X and Y again, we need to go the other way around. We need to compute new values for X and Y. So in a sense, here we have some sort of a forward computation. And later here we have a backward computation. Now, if we read things a bit more, we get the following. Upon calling choose, we introduce in our translation a call to what we call a forward function, which is the same function as before the purified choose. And then upon ending the lifetime alpha, we introduce a call to the choose back function, which recomputes new values for X and Y. And choose back is here, and its body is just the expression we had here. And this is the whole idea of the translation. Whenever we have a function in Rust we want to translate, we generate one forward function and a set of backward functions, one per lifetime. And we use it then whenever we need to propagate updates back into the environment. Now, those forward and backward functions really have to be seen like lenses with the get functions and the put back functions. And this leads to an executable translation, which is, I think, quite idiomatic. So for instance, to take a more complex example, if you have a function which gives you a mutable borrow to the nth element of a list, the forward function is just a get function, which gives you the nth element, and the backward function is just an update function, update the nth element with some new value. And we get similar functions for whatever, all the functions which manipulate tree-like data structures, which are typically what you can implement in safe Rust without interior mutability. Now, something else interesting is that this translation is actually modular. So to be more precise, in order to generate this snippet of code, you don't need to have a look at the body of choose. You only need to have a look at its signature. And this can be seen from the fact that the forward and backward functions, their types are derived by looking only at the signature of choose. So in the case of choose forward, it's pretty simple. We look at the signature and purify everything, typically by removing borrows. So you have Boolean, I32, I32, I32. This is what we get here. And for choose backward, we have the same inputs as choose forward, and we need to take as additional inputs all the borrowed values we returned here, and which need to be propagated back to where they were borrowed from. So here, we returned one mutable borrow of type I32. So we take one additional input of type I32. And then what does choose back return? It just returns new values for the borrows we consumed as inputs. Here we have two borrows, X and Y. So we return a pair of the corresponding types. So what we see is that, in a sense, for the subset we consider, the signature of the Rust function really captures the effectful behavior, because we can characterize the effect of calling a function by those forward and backward functions. And then, of course, if you want to characterize the functional behavior, you need to have a look at the body so that you can precisely define those forward and backward functions. In practice, this modularity is very useful to actually generate the translation and also handle several things like, for instance, the external dependencies. If choose here comes from an external crate, an external dependency, then we just, in order to generate this, we just have a look at the signature, declare the choose forward and choose backward function, and then leave it to the user to precise the implementation or provide lemmas so that it can reason about those. So that way we have an easy way of handling the dependencies. And in the future, we believe it will be very useful to handle traits and function pointers, because we'll just have to consider trait methods and function pointers as opaque functions. So we implemented this translation mechanism, and this leads to the following infrastructure. So on the left, you have the Rust compiler, and we retrieve the mere output, so the Rust mid-level intermediate representation. And because the way the Rust compiler is done, you can only do this by implementing a Rust compiler driver, which links itself to the compiler. And in our case, we implemented something we call Caron. And the thing is, because it is easier to implement and maintain a compiler written in a functional language like OCaml, the translation itself is not implemented in Rust, but in an OCaml implementation. And so Caron retrieves the output of the compiler, converts it to an easy-to-use AST we call the low-level borrow calculus, serializes it, and then Aeneas deserializes it and performs the translation. Now, in practice, Caron is actually completely independent from Aeneas, so it should be reusable for other projects, and it really gives you an easy access to the Rust compiler. So in our case, we'd be very interested in using it to connect our work to some separation logic framework to do some unsafe Rust. Now, for the various backends, as of today, we only have an F-star backend, which is working. The simple reason being that we are originally F-star experts, but we're currently working on several other backends, so Coq, Hall4, and Lean. The translation itself works through some sort of a symbolic execution. And an important point to mention is that in order to make that work, we have to compute the borrow graph. That is to say, we need to compute at every point in the function who borrows what from whom. And because of this, we have two things. First of all, we don't need to trust the Rust borrow checker to do our translation. We do the borrow checking ourselves. And also, along the way to getting to this symbolic execution mechanism, we had to come up with some operational semantics for Rust and its borrow mechanism. And this is one of the contributions of our work. Of course, this is still early work, so we have quite a few limitations. And the main ones are listed as follows. Of course, we only target safe Rust. We have no trace for now, but we believe it should mostly be engineering. And because of the modularity of our approach, we believe we should have it should lead to a quite natural translation. We have no loops. I'm currently working on that, and I'm making good progress, so we should have them soon, or at least some class of loops. And we don't have internal mutability, because this introduces real effects and real aliasing. We would be interested in having this on the longer term, because we like to analyze programs which use coarse-grained concurrency, but this is on the long term. Now, stepping back a bit, something important to mention about this framework is that it is really not in itself a verification framework. That is to say that Aeneas is not something to which you give a program and then you push a button and it tells you everything's fine or there is a problem. It's really a generic compiler pipeline. So what it does is you give it a Rust program and it compiles it to a pure model. And then you can do whatever you want with this pure model. So you can extract it to the available backends. And once this is done, you can state and prove various properties about this pure model. So for example, you can write a program and then prove in, say, Lean, once the backend is done, you could prove panic freedom and functional correctness. But you can also do other things. So for example, if you apply this framework to a Rust implementation of a cryptographic protocol, you might want, so panic freedom and functional correctness are not necessarily what you want. You might want to prove security properties about your program. And it's actually something we've done in F-star on a previous work project called NowStar, which is a verified protocol implementation, and we prove security properties about that. And it should be possible to do that, and we're interested in doing that in the future, proving various security properties of Rust implementations. So we really want to have this generic pipeline. It just provides you a pure model for you to do whatever you want with it. Now, of course, all the implementation is publicly available on GitHub. We presented this work last month at ICFP, and in complement to the published paper, there is a long detailed version which gives all the details about how this works. And of course, please feel free to contact us if you have any questions. Now, I still have a lot of time. I would like to dive a bit into how this translation works, because the high-level ideas are actually quite simple. So as I said, the way the translation works is by doing some sort of a symbolic execution. And in particular, in order to make that work, we need to compute the borrow graph at every point in the execution of the function. That is to say, we need to know at every point in a function who borrows what from whom. And the difficult part here is to precisely abstract the function calls, to introduce the proper constraints between the borrows while not losing information. So let's start with the mutable borrows. Okay, so here we have a very simple snippet of code. We introduce a variable x, borrow it, do some in-place update, do a reborrow, and then retrieve back access to x, which should end the px2 and px1 borrows. Now, in the symbolic execution, we start with an environment where there is a mapping from the variable x to the value 0. And then we can evaluate the mutable borrow operation here. So what we do is we model borrows as first-class values. So here what we say is, as px1 borrows the value in x, we take this value and we insert it somewhere inside of px1, inside some wrapper which says that this value was mutably borrowed. Now, of course, you want to remember the fact that this value was actually borrowed from x. And we do so by introducing here a value mutable loan and linking the loan and the borrow with a fresh identifier L0. So what this environment tells you is that you've got px1, which maps to a mutably borrowed value, which is actually equal to 0, and which comes from there. And then we can do the following. So for example, here we do the in-place update. So we first evaluate the right-hand side, which is a constant, so there's nothing to do. And then we look at the left-hand side. We need to insert this value at the proper place. So we look at px1, it gives us the following. Then we apply the dereference, we dive into the mutable borrow, and we get there. And we're done evaluating the path. We can update this value with a new value 1. So we replace 0 with 1, and we're done. And then we can proceed with the reborrow operation. So we first evaluate the right-hand side. px1 maps to this mutable borrow. With the reference px1, we get it there. And now we need to mutably borrow this value. As we've seen before, when we mutably borrow a value, we simply insert a pair mutable loan, mutable borrow. So we take one, we put it there, we insert mutable loan of a fresh identifier L1, and we wrap one in this mutable borrow to indicate that it has been borrowed. And finally, we get there to the assertion where we get access back to X. So what we do is we want to read X, and we see it has been mutably loaned, which means that if we want to get access to this value again, we need to end this loan, in this case, L0. So we look up the borrow and we see, oh, the value has been reborrowed. So we need to end this borrow too, so L1. We get there and we see, okay, here we have full access to the value, so we can end L1. And when we end the borrow, we simply take the value and put it back where the loan is, which really is like some sort of a hole. So we take one, we put it there. And because we invalidated the borrow here, we replace this borrow with the bottom value, which just means this value is invalid. You can't access it anymore. And now you can end the borrow L0 by doing the same. Now there is one here, and px1 maps to bottom. So what we use is this lazy semantics of borrows, where you end borrows as late as possible. Whenever you have a borrowed value and you need to get back access to it, you end the borrows. And in practice, this actually gives us a borrow checker for some subset of Rust. So for example, here, if you want to, after the assertion, if you want to access back to use px1, this would be invalid. And we would see it because on the right, we would want to access a bottom value, which is invalid. So this is an illegal operation, and we see, okay, we're violating the borrow mechanism. So this gives us a way of handling mutable borrows. The shared borrows are very similar, so I'm going to skip it. And now let's see how we handle the function calls. So I'm going back to the choose example from before. And if we evaluate the beginning, it's pretty simple. Okay, we initialize x, we initialize y, and we borrow them through px and py. And this gives the following environment. X maps to a value which has been borrowed by px, y maps to a value which has been borrowed through py. Okay. Now comes the interesting part. We evaluate the call to the choose function. We start by evaluating the input arguments. True is a constant, there is nothing to do. Then we move px. And by moving px, we consume its value. Okay, we remove the value and we replace it by bottom because as the value has moved, it's not valid anymore. And of course, we need to put this borrow somewhere. We can't just forget it. And we do the same for py. We move the value and replace it with bottom. It has been consumed by the function, and we need to put L1 somewhere. Now, the question is, what does choose return? What do we put in Z? Well, Z has the type mutable borrow of I32. So necessarily, Z now maps to some mutable borrow of some identifier L2, and which contains a value of type I32. And as we don't know what this value is, we just insert a fresh symbolic value as 0. And of course, the question is, what is this L2? Because we know there's some identifier L2, and because of the signature here and the lifetime annotations, we know that this borrow L2 should be linked to the borrows we just consumed, so L0 and L1. So what we do is we put everything in some sort of a bag we call a region. So here we introduce a fresh region R0, and it contains the borrows we consumed, L0 and L1, and the loan link to this borrow L2. This really says, by calling the function, we consumed L0 and L1, and we returned a borrow L2, which is linked somehow to L0 and L1. And actually, in this case, this is L2 is L0, but we don't know it unless we open the function, which is not what we want to do. Okay, so now we can continue the evaluation. There's the plus, which doesn't do anything special. It takes as argument star z. When we dereference z, we get this value. There's nothing to do. The constant 2. And we store the value in star z. So by doing so, we replace S0 with some other fresh symbolic value, S1. And now for the really interesting part, we get to this get access back to X here. So we want to read X, but X has been borrowed. There is a loan. So we need to end this borrow L0. And the corresponding borrow is here in this big bag in R0. And what we say here is that because L0 and L1 are linked somehow to L2, but we don't know how, if you want to retrieve access to L0, to the value borrowed for L0, you need to end the loans in the bag because you don't know how everything else is each other. So we start by ending L2. This invalidates Z. And now we can end the borrows L0 and L1 to reinsert values there. Of course, as through the function call and through this in place update, we may have updated the borrowed values. We replace them with some fresh symbolic values, and now we can reinsert them back what they were. So we get now an environment where X and Y map to some symbolic values out of type I32, and as expected, Z is not valid anymore. So this is how we handle function calls. We introduce those, what we call those regions, which link the input borrows and the output borrows, and really work like magic wands. So the loans are what's on the left of the magic wand, what we need to consume in order to give back what is on the right, which is the consumed borrows. The thing is, once you've got this, it's pretty simple to come up with a pure translation of this snippet of code. So let's get back to the beginning. And now we'll do, while doing the symbolic execution and should be updated environment, we'll also do the pure translation. We start with the first 4 statements. So we initialize values and perform mutable borrows. The thing is, in a sense, initializing updating a value and borrowing a value is just some sort of bookkeeping work on the environment. So it doesn't need to lead to anything in the translation. And then comes the call to the choose function. As we've seen before, whenever we call a function, we need to introduce in the translation a call to the corresponding forward function. So here we introduce choose forward. Also, because in all generative functions may fail, for example, they may panic, we consider panic as failure. I use a modality notation because choose returns a result. So the arrow and the semicolon. Now, what are the inputs to choose forward? Well, they are given by those arguments here. We start with the constant true. Then we have px. So px is this value. As we go into the pure world, we ignore the borrows. So we just keep the 0 here. So we get the 0 there. Then we consume py. It gives us 1. And now the question is, what does choose forward introduce? Well, it introduces the value which we need to put inside of z. As we said, we update z to map to some mutable borrow of a fresh symbolic value as 0. So choose forward returns as 0. And then, of course, we link all the borrows there by putting them in the bag, like this, and we continue. So we have the addition here. We need to introduce the proper function there. On the left, the first argument is star z, which is s0, get a 0 there. The second argument is the constant 2. And we return a new symbolic value that we put inside of z, which is s1. So this returns s1. And finally, we get there. So once again, here we want to read x, but x has been borrowed. I mean, there is a loan here, so it has been borrowed. And we want to retrieve this the borrowed value. And doing this requires to end this region. Now, the thing is, this region is used to abstract the call to choose. So we actually remember that it was introduced because of the call to choose. And when we end this region, when we open it, we introduce a call to the proper backward function, so choose back, with the same input arguments as here, as the forward function. So true, 0, 1. Now, what is the additional argument we need to give it? Well, once again, the backward function, what it does is it consumes the borrowed values it returned and propagates them backward, back into the environment. So here, we consume the value which is borrowed through L2. So we end L2 and look what is consumed by ending L2. And we get S1. So this is the additional value. And finally, what does choose back return? Well, it returns new values for the borrows which were consumed as inputs, so L0 and L1. For those, we introduce some fresh symbolic values, S2 and S3. So choose back returns the pair S2 and S3. And that's the whole idea of the translation. And that's the end of the presentation. Thanks for your attention.
I don't know if Xavier's left already. I'm guessing yes, in which case, does anyone have questions?
I have a question. So I'm not familiar with the pure framework that you're talking about in terms of the target language, but I understand the idea you're saying that doesn't have a notion of references. But I'm having a hard time predicting certain things about filling in the gaps about how the translation of the signatures generalizes. In particular, I don't yet know what happens if you have, for example, a composition of an ampersand mute of an ampersand mute of an integer, and what that ends up meaning in the translated signature.
Yeah, yeah, that's a good question. It's not completely obvious. So maybe I should have put it in the slide. We don't support nested borrows in the signatures yet. I've been working on that, and I think I've got a pretty good idea of what should be done. It's not completely obvious. So the thing is, okay, I'm not going to explain what it would give in the pure translation, because we need to have a look at a detailed example. Now, with regards to the problem of linking the translation to the original Rust code, we have this problem in mind, which is that an issue is, how do you say you translate some program and you want to prove some properties about the program, and you do it on the model. And the question is, how do you write proper specifications on the model so that you prove what you really want to prove about the original program? And what we have in mind is that in the future, it may be interesting to actually implement support for a specification language. For now, we don't do it because we really want to target extrinsic proofs, and because there's supporting some specification language is a big engineering burden. But in the future, we think it would be interesting to have a specification language so that we can actually generate the lemma statements you need to prove. And I think that would help a lot bridge this gap between, make the link between the original Rust program and the generated translation. Oh, and I've just seen Ralph's question, and yes, nested borrows work fine within a function. It's just if it's in the signature, there's a problem. And yes, the symbolic translation is all done at the mere level. We do this for several reasons. So actually, when we started the project, we did like everybody doing some verification of Rust program. We started by targeting the mir. It gives us a lot of very useful things. For example, there is a lot of desugaring which happens before the mir. For example, there are reborrows which are introduced before you call functions, and those are very useful. And the match statements are desugared, and handling them at a high level would be very annoying. Now, the counterpart is that we actually need the control flow to be structured in order to make the translation work. And because of this, we reconstruct the control flow. This is something very annoying to do, and which we wouldn't have to do if we targeted here. But I don't know how we can make it work on the HIR. So for now, we do this control flow reconstruction.
Would you mind if I ask one?
Yeah.
So I was curious about, especially like I heard the word symbolic execution, and I got worried about loops. So in the looped example, what would you do?
Okay, so what we're doing is it's actually in two steps. The first thing is, when you have a control flow branching, we actually we duplicate. So for example, you may have an if then else, and then you may have the two branches which merge again. And for now, we don't merge them. So we actually, it leads to code duplication. So the first thing we're trying to do is, and I think this is almost done, I need to implement it. But I've got the rules written on my computer. So we need a merge operation to merge the two branches. And then the next step is, once you've got this merge operation, the idea would be to have some sort of be able to compute some sort of a fixed point on the loops.
Right.
Because the difficult part is, as we don't have annotations, we don't know how to, we want to replace the loops by calls to some recursive functions. But the problem is, what is the signature of this function? And so you need to find this signature, and because we don't have annotations, we can't use user annotations. So we need to find it ourselves. And our way of doing it is to complete this fixed point, which gives us this signature. And once you start doing that, having those merge operations and those fixed point, it looks a lot like abstract interpretation actually.
Almost like a backwards of like the tail call optimization, I suppose, right? You decompile, compile.
Yeah, yes, exactly. Yes.
Right. Okay. And then if I may sneak one more question in, what's kind of properties, in addition to functional properties, might be interesting to preserve? So if you're going F star, there's interest in doing crypto. And for crypto, I think you kind of alluded to this, like secrecy properties or timing properties. So do you plan to preserve timing in timing, or like say number of like computational steps in the translation, or is that completely outside of scope?
So timing would be difficult because I think if we want to study timing, we would need to have a deep embedding, I guess. And the thing is actually, so yes, I mentioned Neustar, and there are other projects like Hackelstar, which have been verified in Nevstar. And actually, in the case of Hackelstar and Neustar, timing is preserved not through, we don't prove that we preserve timing. We justify it at the meta level by forbidding the use of some operations like division on integers, and we do this by using some interfaces which don't allow you to do some sort of things. And with regards to that, if you want to have a Rust program and for cryptography and prove that it is time constant on the inputs, I think a good way would be to do something similar in the Rust implementation. And actually in Hackelstar, so as we don't have a meta, we don't prove in Fstar that the primitives are constant time. What you have to do is you have to audit the code to make sure that you don't do anything forbidden. You don't use a forbidden function. I think that would be the way of doing that. But there are other very complex properties you can prove, like security properties. And this is done by linking your implementation to some symbolic implementation.
Yeah, so direct information proof, it seems like it's in scope, right? Sorry if I spoke over someone.
In terms of timing, like, literally no part of the Rust compilation pipeline preserves any timing. So it's really hard to say anything on the MER level because it's just not a thing anyway on the pipeline. I think there's some more foundational stuff that needs to happen first everywhere, also including LVM and stuff.
Okay, well, thanks for the remark. On our side, okay, I was not aware of that, but on our side, what we thought of doing actually was to leverage previous work made on, say, Hackelstar, write those in Rust functions, write some wrappers, and then use Rust to work on the protocol level and on everything which is on top, and use the timing from the C functions below, but not redo this work in Rust directly.
I think that's it for me. Thank you, Son, and thank you, Ralph.
Any other question? Sina says,
yeah.
Sorry, go ahead, Daniel.
Yeah, so I was wondering this thing where you bring in regions and so on, right? So you showed that happening for one function call. Sort of what happens when you start having nested calls? Do you end up with an explosion in the number of choices that eventually have to be resolved?
Nested calls, you mean you have one call, then another, etc.
Yeah, so if choose was then calling choose on itself or something, right? If you had some like tree of choices that you made, do you end up with like, do the regions sort of grow without bound, or is there?
Okay. As of today, it's not really a problem. So because you can consider, say, a list n function. So it's it's recursive.
Yeah.
And if you call this function, you really consider it as an opaque function. So it would take one mutable borrow to a list and return one mutable borrow to an element of the list, plus some index, for instance. And so when you call it, it would just introduce one region. And when you translate the function itself, you would have two branches. So you would match on the constructor and then look, okay, if you've got me, you panic. Otherwise, you check the index, and if it's equal to 0, return the borrowed to whatever, to the current element. Otherwise, you do a recursive call. And so here you would have one region introduced for the recursive call. So in the current setting, it's not a problem. It might be a problem when we consider the merge operation and the loops, because the way we're currently doing it is, in the merge operations specifically, we actually duplicate a lot of things. And this leads to, if you have two branches, and those branches you call functions, and then you merge it, it tends to introduce a lot of regions. And then if you try to compute a fixed point, you have quite a few things to do. It might be a problem there.
Thanks. And then, so similarly, but your example, you concretely knew what value was being passed into choose, but I presume it would also work if you had a symbolic value coming in.
Yeah, I simplified a bit, but it works also in that setting.
Thanks.
So Selina asked in the chat, this sounds a lot like 5 functions. Would this analysis benefit from an IR that supports SSA?
I'm not sure. So the main thing is actually with the way we do the translation. So we have this environment, but the environment is really for bookkeeping. So we have that X maps to something. And this is really this something which is important. And then for example, we evaluate star PX, or we evaluate nmut of X. And this gives us, and we use those variables to look up the values in the environment. But what we're really concerned about is having those unique identifiers of borrows and those unique identifiers of symbolic values. And actually, if you look closely, the translation doesn't directly manipulate variables like x, y, or px, etc. It manipulates the symbolic values. And then we have some heuristics to find proper name for those values. But it's really concerned with those which are not really, are a bit orthogonal to, I think, having, say, an SSR representation.
Thank you. Anyone else has questions?
Sure, I can ask one. So you've already kind of implied the answer to this question, but it sounds like you're compiling down to pure and then asking people to use a theorem prover to reason about this compiled code. How bad is that experience?
Actually, the reason why we do that is that we had a pretty bad experience at using SMT solvers in the past, and we really want to escape that. So to be more precise, there are some problems on which SMT-based frameworks are very, very good. Like, say, it was very good for Hackenstar, where you have the cryptographic functions. And what you do is you actually just prove that your implementation, which doesn't manipulate, well, the management of memory is actually very simple. And you just prove that they refine some specification, which is actually very close to the implementation. And along the way, we get a lot of things like memory safety, etc., because you prove things. But so we started with that, and it works very well on this. And the control flow is also very simple, which makes things manageable because, for instance, you have less paths, so less explosions, etc. And we tried to. So I mentioned the project called NoiseStar, and which studies a family of protocols called noise. And the reason why we studied that is we wanted to verify an implementation of the WireGuard VPN. And when we got towards more complex data structures, because the WireGuard VPN is a protocol plus a lot of things, very high-level things like create a device, a peer library, some parallel workers, etc. And when we got into that, the SMT solver just was a huge barrier, actually. And we got into a position where we really wanted just to have a context and be able to manipulate that context. And there's something, I think, which is very easy to conceive, which is that the SMT solver can help for a lot of things. So for example, in the case of cryptographic primitives, it helps a lot for the arithmetics. But the more we moved on, we went higher up the stack, the less we used that actually, the less we needed to have a good solver for arithmetics, and the more we need to just be able to see a context and manipulate this context and open invariants and not do this by hand. Because what often happens is, you want to prove an invariant or a precondition and it fails. And so you need to check, oh, what fails? I don't know what fails. So you introduce proper assertions. You need to instantiate those by hand. It can be very, very cumbersome. And really in those situations, having a theorem prover with which you can interact is a lot better. Now, I don't have yet an example that I can show to compare the differences. It's actually something I intend to do once I get one more backend, and the link backend will probably be the first finished. Because for now, we only have the F-star backend, and F-star is based on an SMT solver. But yeah, so the idea is really like, so you asked how bad is the experience, and I would say, actually, I think the experience is rather good. And from my personal experience on previous projects in Coq and in Hall 4, there are situations where the experience is better when you use a theorem prover than when you use SMT solvers, and it all depends on the kind of program you verify.
So I like that answer, but I'm also questioning like the distance from the original code to the code that you're actually reasoning about. Does that prove a problem in your experience so far?
Okay, so far we've verified a small library of hash maps. The reason being that, so it's resizable hash maps where you have an array of linked lists, and so you hash the key, complete the modulus, modulo the length of the array so that you insert it somewhere, and you leverage the fact that you shouldn't have too many hash collisions, and when you start having too many elements in the hash map, you resize the array by doubling its size. So we did that because, to me, it's really the minimal example of a data structure which is imperative and on which you have some high-level specification to prove, because you really want to see this map as a map. So far, it didn't prove to be a problem. The translation seemed to be quite natural. But of course, the example is very small. It's just 200 lines of code. And we'll need to see on more complex example how it works. My intuition is what's really important is that we manage to make the link between the signature of the function and the types of the forward and backward functions. Because this is really where what you want to look so that you properly write the lemma statements you want to prove. And then once you've got that, you can have a look precisely at the body, see what proof obligations you have. And that, I think that is, so far it's manageable. But once again, we need to see that on a bigger example.
Thank you.
Valdemar, I hope I'm pronouncing this right. Valdemar is asking, does the low-level Borrow calculus also have these limitations, such as no loops?
No, the LLBC is really meant. It's just an easy-to-use, clean AST for Mir. So it actually, it's Mir. It's Mir reconstructed. So we don't have this restriction. It's only in the translation mechanism that we forbid loops.
I'm going to jump on that, asking another question to which I already know the answer, but I'll ask it for everyone. If I want to use LLBC for my own analysis, is that possible? Do you plan on allowing that to people?
So yes, really intend to make it available to people. And actually, following a discussion with Sasha, I've been doing a lot of engineering work to improve what we have, provide many options, for example, to give to the user the possibility of choosing the low role of Mir we want, for example, built Mir, promoted Mir, optimized Mir, and also we do the reconstruction. So we actually translate Mir to some unstructured LLBC, and then we reconstruct the control flow. And I want to give access to this unstructured LLBC because you don't always want to have this structured control flow. And I'm turning the whole thing into a library. So yes, I'm very willing to make it available to people, and please feel free to contact me and also submit PRs if you want to add features. And I'm currently doing, once again, a lot of engineering to make the whole thing usable by other projects.
Thank you. We have time for 1 or 2 more questions. If nobody has one, I have one, but all right. Well, you mentioned that your translation gives a semantics, lazy semantics to borrows, and obviously the other semantic model of borrows is stacked borrows, and I don't know what's the name now, tree borrows. Ralph will correct me if I'm wrong. Do you know? Could you prove, for example, that you're strictly stricter than that because because this is the, let's say, current accepted model of aliasing in Rust?
I think it should be possible to link what we do to the stacked borrows, because actually, so the way I see it is, what we do is actually looks a lot like the stacked borrows, which are also lazy from my understanding. The only difference being that the stacked borrows look at an unstructured memory. And on our side, we don't want to model the memory as, say, an array. We want to have this very structured view where we have borrows as first-class values. But I think it should be possible to prove that we are stricter than the stacked borrows.
I mean, that would basically be a soundness proof, right? Like showing that this type system accurately models a UB-free subset of Rust, or this operational semantics.
Yeah.
Yeah, I mean, stack borrows obviously wants to talk about unsafe code. So
yeah.
Just,
but so it would be nice to show that you're strictly in the safe, for the safe subsets. This translation is sound with respect to that.
Yeah, I mean, as a start, I think it would be nice to show that it's sound with respect to a machine that has a heap. Like, I would argue this isn't really structured memory. It's actually just no memory. It's just an environment. It's a bit of a funny one because of these lone lookups, but it doesn't really have the usual features that I would expect a memory to have. So one could imagine also just giving a memory operational semantics to that language and showing that it agrees with the kind of environment-based one on well-typed programs.
All right, if we have one last question, we can ask that, otherwise we might close the session. It's been 58 minutes now. Thank you very much, Sean. That was really interesting. And I think next month is Ralph's talk, so see you then. And of course, thank you to Xavier for organizing this session again.
Okay, thanks everyone.
Thanks, Sasha, for taking over.
Of course.
Thank you.